Hi everyone. This week we will study lattices from the algebraic function fields. Particularly, I want to show you how we can construct lattices from function fields in general. But mainly our purpose will show that we'll investigate the lattices from elliptic function fields and lattices from what we can conclude from the lattice constructions from hyperelliptic function fields. Mainly, I will follow these two references. Both of them are published in finite fields and their applications. I should mention that Dr. Atesh's PhD thesis is a nice pedagogic introduction to this topic. For this purpose, let me remind you some basic notions like we studied last 5 weeks. We studied the function fields as a field extensions. We used the field theory, algebra, and linear algebra. But later on, the most important invariant was the genus, which in some sense measures the complexity of our structure, global structure. And it was defined via Riemann-Roch spaces, as I remind you later. And here, by the genus, by the G, we mean the genus of the function fields. And the first fundamental notion we studied was the places, and the set of places was denoted by P of F. And indeed, we have shown that this is a non-empty set. And but even though the set of places are not non-empty, during the lecture I mentioned that the set of the rational places might be empty, but for the elliptic function fields and the rational function fields, particularly in their characterization, we have seen that there exists at least one rational place. But here in the lattice construction, we will be interested in the number of the set of rational places, so its cardinality. There is an important fact, like we will be considering the lattices function fields over the finite fields, and in this case, this set is always finite and non-empty. And the other important object we have studied was the degree zero divisors, quotient principal divisors. We have seen that every principal divisor is degree zero divisor, but we don't have the other way around if F is not rational function field. In this case, again, if we are working over the finite fields, this quotient group is finite group. And we will denote this quotient group by the class 0 group. And particularly when we were studying elliptic function fields, we have seen that this set provides the group structure of the elliptic function fields. And here we will be interested in their cardinality, so their group order, and we will denote this group order by H. And we will define it as the class numbers of the function field F in general, not only for the elliptic curves. And the most important geometric object inside of a function field was the Riemann-Roch space for a given divisor D. We define the Riemann-Roch space as a set which contains the functions such that their principal divisor plus the given divisor D is positive. Indeed, we have seen that this is a finite dimensional vector space, and its dimension provides important global invariants such as genus or the canonical divisor. Here by the genus, we mean the same thing in the statement. And genus and the canonical divisor they are strongly related to each other, connected to each other. And for the canonical divisor, dimension of the canonical divisor or dimension of the Riemann-Roch space of a canonical divisor, we have seen that it is indeed the genus G, and its degree is 2g minus 2. And for a divisor D, we have also defined its support, because we know that a divisor is defined as a collection of the finitely many places. So that means this is a formal sum MPP with finitely many non-zero integer coefficients. In this case, the places which appears with the non-zero coefficients gives us the support of the divisor D, and degree of the divisor is defined as the sum of NP times degree P, where degree P denote the extension degree of the residue class field of the place P over K. So in this case, this is going to be FQ, and we have seen that this is always finite, so degree D is a well-defined notion. And for the computational aspect, like because the places and the valuation rings were purely algebraic notions, but for the computational aspects, we correspondingly studied discrete valuations, discrete evaluation maps inside of the function field. Here we will denote it by VP by associating a given place P. And if we are given a non-zero transcendental, we have seen that it has at least 1 zero and 1 poles. And for a constant, we know that it has no zero and no poles. But in any case, for non-zero function inside of a function field, there was a way to encode all zeros and poles into a divisor, which is called the principal divisor. And that was defined as the zero divisor minus the pole divisor. And here, recall that zero divisor is defined as the sum of VP offset sum times P, where VP is positive because P is a pole of P is a zero of Z, and this is the pole divisor, which is defined as the minus VP of Z minus sum of the VP offset sum times P, where P offsets are negative because we want to encode all poles offsets into a divisor, and note that both of them are positive divisor. And indeed, like the all principal divisor is elements in the the principal group of a function field, and we have seen that every principal divisor is a degree zero divisor, and this fact is based on the observation, which tells us the degree of the zero divisor and the pole divisor are exactly the same, and this is equal to the extension degree f over the transcendental z. Here, by the degree of z for non-zero function, what we want to mean is it's the degree of its zero divisor, or equivalent the degree of the pole divisor. And by using these definitions, indeed, we can denote this notion, this integer, this quantity, as 1 over the sum, 1 over 2, half of the sum, absolute values of the valuations of z's time degree p. It will be useful when we want to derive some parameters for the lattice constructions, lattices from function fields. And in the last exercise, you have seen another invariant for the function fields, which is defined as the minimum extension degree over a rational subfield. And in the last lecture, I tried to give the motivation as follows by considering the elliptic function fields. Recall that we define the elliptic function fields over K, where X and Y are transcendental over finite field FQ, but they're in the algebraic relation as y square equal to f of x, where f of x is degree 3 square-free polynomial. And in this case, we have observed that its extension degree over the rational function field over fq of x, like with respect to this transcendental, is 2, but its extension degree over the rational function field fq of y was 3. And in this case, like the extension degree over the rational function field is not a well-defined object, so it works differently from the algebraic number fields. But I mean, in this case, we can consider the minimal extension degree, and this is defined as the quantity, and that will be the this quantity will be also important when we study the parameters of the lattices, lattice constructions. We know that in the rational function field, we have the full characterization of the places. In particular, for the notation, whenever I use z equal to alpha, what I mean is the place which is 0 of the linear polynomial or transcendental z minus alpha. And by z equal to infinity, what I mean is the pole of z, but during the lecture, we denote them by these notions. And in the last week, we study the function fields. If we know everything about the rational function field, one of the basic ideas study the function fields in general, just to study by viewing them as a finite extension of the rational function fields. This is also coming from the definition. Its definition, particularly if we know everything about, if we have full characterization for the places in the rational function field, the idea was to study the similarly places in the extension field by relating the places in the base field. So for the general, let me denote it by F. Let me denote this algebraic. In particular, we will be interested in finite extensions by F prime. And we have seen that if we are given a place in the base field, we have finitely many extension places, and we use this notation. And if we are given a place in the extension field, we know that there exists unique place which lies under P prime. And recall that we related these two places with some invariance. And the first invariant was the ramification index. It depends on the places P and P prime, and that was defined as the positive integer, which gives us the equality between the valuations of a function, non-zero function, in the base field F and the valuation with respect to P and P prime. Particularly, it was if we have a prime element of P, E was defined as the VP prime of T, because I mean, by the definition, we know that P is a subset of P prime, so prime elements, its prime element is also element in the P prime. Its valuation should be positive, but it can be strictly bigger than 1. And it gives us some sense like how the factorization behaves in the extension field for a given transcendental X. And the other important invariant or the quantity which relates this places P and P prime was the relative degree or the inertia degree, because we have seen that if P is a subset, like P is a subset of P prime if and only if their corresponding discrete valuation rings satisfies these inclusions as well, or if and only we have such a non-negative integer E. But by using these two properties, we can see that residue class field of P in F is a subfield of the residue class field of P prime in the extension field F prime, and this extension degree is defined as the relative degree. And we have seen that if we have a finite extension, this quantity will be finite, but we can't conclude this bound always. So it can be also infinity, but we will be in this case. This is the ramification index, and this is the relative degree. And of course, depending on the P prime and P, relative degree of P prime over P. And why these notions were important? Because we have seen that another global local relation can be given in terms of the ramification index and the relative degree. And we gave it under the name of fundamental equality. That tells us, indeed, the extension degree in the case of finite extensions of function fields can be denoted in terms of the sum of ramification indexes and relative degrees. Here we should be careful. This equality works for any given place P, and its extensions P prime, or more explicitly, what you can write. We know that there exists finitely many extensions Pi primes of P. That means this extension degree is equal to sum of ramification index times the relative degree. And in the next lecture, I will introduce some basic notions, basic definitions for the lattices and the invariants. And then later on, we will define what's called function field lattices. So see you in the next video. Bye-bye.